Okay, so the next problem in the lead code we are solving is unique paths 2. Okay, so basically this problem is about like I mean we have a robot in the first index. Okay, we have a robot here and it needs to traverse from starting node to the end node. Okay, so we need to determine how many number of unique paths there are that are there on the grid. Okay, so basically just by visualizing it I can say that this is the one path and this is one path, there is no other paths, right? So basically like this is a blockage, we cannot enter here. So if there is a blockage, avoiding it, we can go it only by two ways, correct? And also if you're solving this grid based problem for once, so basically this traversal will be ideally most of the cases what it will be like, it will be left or bottom. Okay, this robot can traverse only in this direction. Okay, and there can be like I mean a number of directions also, like that's also possible, but in this problem at least the traversal how it can traverse is either to the right or either to the bottom. Okay, so now how to solve this, right? This is nothing but a graph problem, right? Like I mean we have a starting node and we have a ending node, and also these are like nothing but a connected nodes. Basically these are connected such a way that it is connected to the right, it's connected to the bottom nodes. Okay, so this is nothing but a graph problem. So what we can do is we can apply traversal algorithms to traverse from starting to this one, right, starting to the end one. We can do it, and again that will be in a kind of a recursive way, right? We'll be solving it. And now what is the problem here is, let's say that for now let me clear this quickly. So let's say that this looks good, correct? There was only two paths, but let's say now if you remove that blockage, right, let's assume that there is no blockage, what will be the path look like? It will be looking like this one. Like I mean there can be one more possibilities, and this is one possibilities, and it can come from here. Okay, it can come from here, or it can come from here, or it can come from here. Okay, like if you just look at this one, right, there are like too many operations that we are doing it again and again, right? Let's say that once I visit this node, right, once I visit this node, I will be keep on going to this node, right? Like I will be repeating the same operations again and again. Like that is a problem with respect to the this backtracking or recursive solutions, right? So we'll be trying to do the same operations again and again, right? And we know that we can improvise this approach, like I mean by caching this operation, correct? Like as we are doing this operation again and again, so if we store it somewhere, like we will cache it somewhere and then reuse it again, right? So such that we can improve the, we can reduce the number of operations and also increase the time complexity, right? I mean sorry, decrease the time complexity, right? So that's why like I mean whatever we are talking about like caching and everything, we call it as a dynamic programming, right? So now how to approach this problem via dynamic programming, that we will see. Okay, now let me clear this out. And also one more thing is like I mean how did we even know like we can solve it via dynamic programming, right? So one common pattern that I am observing is all this path related sum. Okay, the traversal, like, or it can be traversal, or all the problems that can be solved by recursion, and like minimum path sum, all these problems are can be solved by a dynamic programming. Okay, this is the pattern that I am observing. You can also look for it. Okay, so now, right, like how to like for a dynamic programming we need to build a cache. Okay, basically we'll have to initialize the cache first, and then we'll have to um, update the cache and use it for the next operations, correct? Now we need, for that we need to know like what to travel, what like I mean what is dependent on what, right? That we need to know first. Okay, so let's try to look for a result. Okay, let's say that this is here we are. Okay, like how are we going to identify this result? Basically let's say that if I'm looking only at this point, so what is the ways that I can come from, right? I can come from this way or I can come from this way. Okay, so now let's say that if I already knew how many number of paths joining to this, how many number of paths come joining to this, okay, from the left or from the right, right? If I already knew it, I can simply take a sum of it, right? Let's say that here two paths are joining. Okay, here let's say that some there is some combination. Okay, let's not talk much about here. So okay, let's say that there is one more grid here. Okay, so one joined from this one and one came from straight. So okay, now it is telling that it has two paths joined. Okay, so now what does it mean is, so if you already knew it, right, if whatever the number of paths that is coming joining here, whatever the number of paths that are joining here, I can take simply the sum, right? I can send it as a result, correct? So from the top, like there are three paths joining in, from the left there are three paths joining in, I can say 3 plus 3 is equal to 6. Okay, so now okay, now I said it is a 3 3, like we need to identify again 3, right? Like we know that that's what we are doing now. If similarly, in order to in order to identify how many paths that we are joining, I need to know how many paths that are joining coming from the right side, sorry, from the top side, how many paths that are coming from the left side. There are only two possible ways that we can come here, right? But this is blocked, so this will be 0, we need to check ask the, like I mean from the top guy we need to check like how many paths that are joining. Okay, and to get the answer you will have to depend on again on this one, correct? And for to get this answer you will have to dependent on this one. So basically you can see that chain, right? Basically, to keep it simple, like like I mean for any node we can go to that node either from the top side or from the right side, right? This is the way or this is the way, correct? So if we already knew how many number of paths joining to this, how many number of paths joining to this, we can simply take a sum. That is the overall takeaway from this problem. Okay, now what we know is we know only one thing at this moment. So when we start the problem, right, we will be knowing only one thing, that let me clear this out. Okay, so now we know that we, like I mean we can need to rely, we can rely on the top and left one. But at when we start a problem we don't know anything, right? Basically, like I mean this is depending on this one, this is depending on this one. So finally where are we heading to? We are depending everything on this one. Okay, so it suggests that we are going to build this first to get a solution for this one. Okay, so we'll identify the number of paths that will take to reach this node. Okay, there is nothing but we are here, there is only one path it will take to reach this node. Okay, like it's a start, right? It's a base condition, like, okay, so we'll set it to one. Okay, so now for this one, what is the number of ways that it will take to reach one this one, right? So there is nothing coming from the top, so it only depending on this one. So the 1 plus 0 will be 1. So again we'll apply the same thing here. There is nothing here, so will be only 1. 1 plus 0 will be 1. So similarly here, 1 plus only from the top, then nothing coming from the left, so it will be 1. So if you here also, top will be 1 contributing to 1, left nothing. Same thing here, left nothing. Okay, here also left is contributing to 1, top is contributing to nothing, 0. So finally we ended it up like this. Okay, here is also 1, here is also 1. So now for this one, top is also contributing to 1, left is also contributing to 1, so the final answer is 2. So here we will finally set it to 2. So as there is so this is what we are looking for, right? The number of paths and number of paths that we can build. So finally this will be the answer for us. Okay, so to summarize here, to revise, we'll see one more problem to revise. What we are checking here is so basically we got to know that this is a grid and this is a graph problem, and this can be solved by a recursion. And but as we can see, like there will be too many duplicates, it will increase the time complexity. Okay, to solve the time complexity, as this is a recursion problem and also it's a path problem, we are traversing from here to here and there are multiple duplicate operations that we are running, we thought of using a dynamic programming, right? And from the dynamic programming we know that we need to cache something, but we don't know what to cache. Like I mean it's like we need to check the dependency, what is depending on what, right? So once we check, we know the dependency, let's say that if x a is depending on a b, we need to solve a b first to get a, correct? So that's what we are trying to identify with the dynamic programming here. So what we did here is, let's say that we'll end up in a finally um, like I mean we went to the end node and we'll see like what are the what do we need to get this result, right? We need a, like I mean if we know, already know number of paths that are coming here and if a number of paths coming here, we got to know that it's easy for us, right? We can take a simply sum of it, correct? So similarly then we went here and we did the same analysis, and for that we need to an answer for this. For to get an answer for this, we need an answer for this. Okay, and to need an answer for this, finally we'll be needing the answer from this one, correct? So that's why we got to know that we need to get an answer for from the first node first to get reach to the end, right? So we started from here and analyzing it, and the base condition will be 1 because that is the that's also path, right? We can consider it as a 1, right? Okay, so that will be one path, and from there we started analyzing it. Okay, now quickly check one more problem, and that will make it more clear, and then we can check the code. Okay. Okay, so now, right, I just removed the blockage. Okay, so now we get to see that all the combinations. Okay, that we'll see quickly. Okay, so initially we know that we need to set a base condition. Okay, this will be 1 because it cannot be 0, right? Like if I'm coming there, that is also one path. Like how many number of s, that will be 1. Okay, so now let's try to solve the problem. So what we are going to do here is we'll go here. Okay, is there anything that is coming from the top? Nothing, right? So we need to take a sum from only from the left. So this will be 1. Okay, again here, is there anything that is coming from the top? No, only from the left. So 1 plus 0 will be 1. Okay, next we'll come here. Okay, anything from the left? No, only coming from the top. This will become 1. So when we come here, it like I mean there is an item from left also, there is an path from the this also. So now total path will be equal to 2. Like if you visualize it here, right, if you can see it, we can come from here, or if you can come from here, the maximum paths will be 2, right? We already calculated it now. So if you check it here, so left is saying that there are two paths joining in. Okay, yeah, that is correct, right? We are joining, this is one path, this is one path. Left, we asked the left guy, it said that there are two paths that are joining to this node. We asked the top guy, it said that there is only one path joining it. The one path is this one, correct? So will 2 plus 1, finally it will be 3. So you can also actually visualize it, what are those three paths, right? One is this one, correct? Another one is this one, or the third one is this one, correct? Totally three pass. Our answer is correct so far. Okay, so next thing is we'll go here, and what is the left, any path? No, only from top, so it will be 1. 1 plus 0 will be 1. So here if you can just check, from the top side we are getting a two paths, from the left side we are getting only one path, so answer will be 3. Again, let's visualize like what are those paths, right? Here we're getting the 3. Let's see that if here actually there is a path 3. One path is 3 this one, right? From the left side it said one path. Okay, we are good here. From top we need to get a two paths now. Okay, so let's say check, this is one path, right? This is one path, and also this is one path, correct? From the top it said two paths, these are the two paths. Okay, finally we are here, we got 3 here and we got 3 here, correct? So answer will be 3 plus 3 will be, answer will be 6. Okay, so nothing but whatever the three paths that are coming in this side, right, whatever we that is drawn in blue will join here, that will contribute us to the 3. And whatever that is coming in green here, right, that will also come here, the total path will be, answer will be 6. Okay, this is this problem. Okay, like getting the unique path sum. So basically, like one takeaway from that I am observing is, whenever there is a path problem, right, you can just analyze what is depending on what. Okay, so if you get to know that either we need to solve the problem from top, or we might need to solve the problem from the bottom. Okay, so once we get to understand that, it will become easy actually to solve it. Okay, so now if the algorithm is clear, I think there is nothing much to see here actually, so we'll just see quickly. Okay, so we need to handle this condition. Okay, let's say that what if the entry itself is blocked, right? Like there is one test case that we will, this blockage will be present on this only. Okay, so we need to handle that. Like if the entry itself is blocked, like what is there to proceed further, right? We can simply return 0. Or if the ending is blocked, like we cannot exit it, that's also there's a waste of time to process it further. So we'll do the check here. Okay, yeah, and also like I think I didn't talk about this one actually. Like if there's a blockage, right, they represent it as a 1. Okay, if there is no blockage, they represent it as 0. Okay, so if you can check it explicitly, check it for if it's equal to 1, that's not necessarily needed. Okay, if either of them is blocked, we'll simply return 0. Okay, next thing is we'll set our base condition, because it will be kind of different, and we need to know that initial value. So it's always like in the DP, we'll initialize, we will set a base condition. Based on that, we'll proceed with the calculation. So we'll set the base condition here. Okay, once that is done, so we'll be iterating just like what we did, right? We'll iterate from the this one and this, right? So we'll be calculating the result here. Okay, so what are we doing here? First thing is, if the obstructor is already set, right, like we have already set the base case, we should not touch it, so we'll continue it. Okay, and wherever it is 1, right, if it is 1, it means there is a blockage, we need to replace it with the X. Okay, like if we encounter that. So or else, let's say that if we encounter any 0 spot, what we'll do is we'll get an index of the top and index of the left. Okay, this is what this will give us that. Okay, one is I minus 1, one is j minus 1, so that we'll get top and left index. Okay, and here we need to make sure that the index doesn't overflow. For example, here, right, this has become too much dirty, but please bear with me. Okay, so let's say that we are here. Okay, we need to read it from here, but here this is not a valid index, right? We need to make sure that there is no overflow. Okay, so we generated an index, we need to make sure that's a valid. Actually, X should also be greater than 0, Y should also be greater than 0, and it's not an obstacle. Okay, if the top is obstacle or left is obstacle, we need to skip it. If all these three conditions are met, we'll be incrementing our path sum. A path, what is this? The unique path count. Okay, we'll be incrementing it ultimately after solving this recursive, right? Whatever we discussed so far, ultimately, like whatever the result we get it in, and we'll store it in the same array that will return. Okay, and also actually ideally what we do is we can create a separate DP array, okay, dynamic programming array, to store the cache. Okay, but here what I'm doing is in place update, so you can just make a copy of it, or you can initialize everything to 0 or whatever, and wherever it is 1, you can set it to X. You can do it either way around, but here what I'm doing is I'm doing the in place update. Okay, that is it. Thanks.